Okay. Good afternoon, everyone. Welcome to the afternoon session, the first afternoon session in the embedded track today. This afternoon, we're going to have Stephen Arnold and David Burr, Donald Burr, talk about embedded Linux development using the Yocto and OpenEmbedded system. Welcome, Donald.
Hello. So, how many here are familiar with Yocto? A fair amount. How many here have never heard of it before today? Excellent. Okay, so so I guess to start, we should really talk about the bad old days of embedded Linux development. This is sort of the Wild West where we had all sorts of different monolithic embedded Linux development SDKs. A lot of times they came in like these ginormous tar balls full of binaries. Each vendor had his or her own different standard. They didn't interoperate, and integrating them into automatic build systems was extremely painful. So yeah, it was pretty brutal, and there are some pretty bad ones that I've worked with. Not to name any names. Caveat. In an effort to solve this problem, a bunch of engineers got together and started developing some early, attempts at more of a sort of a standard embedded development frameworks. Started with OpenEmbedded, which is actually still around, which then sort of morphed into OE Core, and eventually became part of Yocto. And we had other people, another track, Debian, which is really hard to say, especially if you're drunk, which sort of begat Angstrom Linux, which then turned into Pocky. I guess it's Pocky. I used to call it Pokey, but no, it's not apparently. Some of these are still around. OE Classic still exists. It's part of Angstrom and Linaro. But Yocto has sort of become the official umbrella project that going forward handles all the Pocky and OE Core stuff. And Steve, feel free to elaborate if if I'm missing anything.
Well, those two things are basically the framework and the distribution. So the bottom one, the Angstrom and whatnot, those are different distributions of OpenEmbedded.
Right. Okay, so Pocky is the umbrella organization that's under the auspices of the Linux Foundation, so we've got some pretty good support there. Corporate sponsorship. OpenEmbedded and OE Core, they're basically more or less synonymous. They are Meta OpenEmbedded, which is one of the layers used within Pocky, and OE Core, which is standalone. Are kind of one and the same. They basically sync across themselves. There's some other Yocto organizations, people who use it. Mentor Graphics, Linaro, Intel, TI does a lot of work with the Yocto stuff. Udo, which is a cool board. Basically, it's like a Arduino combined with a there's also, of course, Raspberry Pi and BeagleBoard, which is the BeagleBone, the new BeagleBone Black, and so forth. So sites and documentation, the primary site was yoctoproject.org, and you can basically find all of your documentation and your downloads under there. Let's see, next. Build host requirements. Now, unlike, Yocto it's not a distribution. I mean, you can't just put it on an SD card and boot your Raspberry Pi with it. You basically have to run it on a Linux host computer, your Intel desktop or laptop, and based on your, how you configure it, it'll build a custom. Basically, it'll build the contents to load onto an SD card based on whatever bits and pieces that you specify that you want in it. So in that way, it's kind of like a Gentoo versus, as opposed to an Ubuntu, where you actually have to build the packages and so forth. As far as build host requirements, on the host, pretty much works with all distributions, Red Hat, CentOS, Ubuntu. You're going to want to make sure that you're basically set up for building. So in the Debian and Ubuntu world, it's basically installing build essentials. There's a couple of other packages that are needed. All of that, of course, is in the Yocto documentation.
Right. The quick start will tell you what your different distribution requirements are, and there's on the OpenEmbedded wiki, there's also an OE core or OE and your distro that will mention some of the unsupported distributions.
Right. And now, as far as obtaining Yocto, there are tarballs at yoctoproject.org, but I don't know, Steve, would you say the best is really to just track the GitHub?
Yeah, I mean, I've been building off of master directly out of their Git repo for the last couple of years.
So yeah, basically.
So master sometimes gets a little bit wonky, but mostly it's pretty good. Normally you would choose a release branch, so you can choose the Daisy, Dora, whatever release branch you want. Hopefully the latest, but you don't have to.
Right, and if you're looking for at a specific supporting a specific board, they might say requires the Daisy release or greater, for example. Supported supported targets. That would be what?
That's a big question. The main supported targets are the ones in the primary Yocto Pocky release, and so out of the box it supports QEMU, ARM, MIPS, x86, all those, BeagleBone. There's the Edge Router Lite. There's a handful of embedded machines that are built into the core distribution of that. So, but then you need, depending on the board, you can get BSP layers from your vendor for your board.
For example, if there is a layer Meta Raspberry Pi for the Pi.
So there's a BSP layer on GitHub for Raspberry Pi. That's one of them. And then SCaLE has a whole set of build scripts and a repo manifest for generating the Pocky open embedded stuff to build for SCaLE, like an IMX6. So you can build your WAN board build with OpenEmbedded also.
So Yocto is based on a tool called BitBake, which is sort of the heart and soul of it. And what BitBake does is it basically processes a bunch of what are called recipe files, and uses those to build various pieces of software. So at the core is the recipe file itself, which is in a way kind of like a make file. It basically is a file that lists, okay, what is this program? Is it name of program like glibc or whatever, and where to download it? It lists a checksum so that the tool can make sure that it downloaded the correct file. If it's a fairly standard package, configure, make, install, you pretty much don't need anything else. But if you're dealing with a package that needs sort of special configuring or patching, there's facilities in the BitBake recipe to do patching, to do custom configuring, building, installing. It's really quite versatile.
If you've ever seen a Gentoo eBuild, it's very similar.
Now, recipes are organized into layers, and layers are historically they're named meta something. So, for example, I believe the core is meta Pocky, or is it?
Well, it's everything under Pocky there's just a meta directory with the
yes,
core stuff.
It's plain meta. But then you have other things like layers. For example, meta multimedia contains a lot of multimedia packages. Meta rather than the board support packages for a given board are usually distributed as a layer, Meta Raspberry Pi. And, the cool thing is you can actually, create your own layers. So if you're a company that you're building embedded Linux-based devices, routers or whatnot, you can create, your own Meta, megacorp layer and put your own custom packages in there and reference that. Core images are is Sato, is that?
Yeah, I mean, there's several. Am I even coming over this thing at all?
Yeah, come on over.
Check 1, 2. Does it? Is it? Okay. The core images that are available are mostly demo images and lightweight console/dev images. So they're not particularly useful for your custom thing that you want to build, but it's very useful for making sure that you can build something and then getting something up and running on your machine. And then you can customize the image to add development tools, debug stuff, whatever it is that you need.
For example, like the classic, the step, sort of the getting to know Yocto that you see in the documentation basically leads you through building what's called the core image Sato, which basically builds a completely bootable image with this sort of little graphic user interface in it, which you can then run under a QEMU to test it and experiment with that.
Yeah, that was their big desktop demo image, the Sato one, but there's now a Weston image.
Oh.
So I think that's going to replace the Sato one as kind of the graphical demo image. There's a Qt5 demo image that has a bunch of stuff in it too, but it's not very useful for anything. It's literally just some demos.
All right. And let's see. Now, creating images. Of course, if you want to, you can totally create your own recipe totally from scratch. But because it's an extendable system, if you can actually extend, an already existing recipe, and that's where BB append comes in. There's also prepend and append, and Steve, can you elaborate?
Yeah, so the meta skeleton is their layer to show you some example package recipes for specific things. So it's kind of a real basic skeleton to create your own layer, your own meta layer. Not a BSP layer. There's a whole BSP developer guide that will walk you through creating a BSP layer for a machine. But for the most part, you shouldn't have to do that unless you're trying to build for a machine that's never had OpenEmbedded built for it before. Right? So if you buy something, typically the vendors do have something available. But so prepend and append are how you would, and this is where it's different than Gentoo. Because in Gentoo, you would copy an e-build to your own overlay, make your modifications to it, and keep building out of your overlay. With OpenEmbedded, instead of copying it to an overlay, you add a BB append to your overlay. So all that does is add maybe one particular custom task to the existing recipe, and you don't modify the existing recipe. And so the prepend and append is similar, but within a recipe, you have tasks. So you have your do configure task, your do compile task, your do install task. And if you just need to make one minor modification, instead of copying the whole task out of the other recipe, you would do compile append and just add your custom thing to run at the end of the normal compile task. So that's how you customize in the OpenEmbedded world.
And again, as far as custom layers go, you can create your own layer for, if your organization is uses certain software as part of its products. Or if you're creating a new board, you'd create basically the way you would do a board support package is by creating a layer, such as Meta Raspberry Pi, and if you do that, for heaven's sake, put it up on GitHub. Finally, new platforms. If you want to kind of create an entirely new platform, there's some examples in the Meta skeleton, and I think
so those colors are horrible. They were better on my computer, but that under custom layer, it has the link to the layer index, layers.openembedded.org. So that's where you would go to look for additional application layers and other BSP layers to see what's available.
All right, and Steve, are we going to do a demo?
Yeah, we can fire something up. We have another set of lovely slides as a handout. So you have the other slides on there? You want to bring those up?
Yeah, let me do that. Oops, wrong button.
So I have some builds on this machine, but when I plug it in, it's going to make my laptop display go black. Yeah. We sent them in to the SCaLE people, so they're going to make like a USB stick or put them somewhere for you to get at them. So they're also on GitHub now. If you want to look, are they in the VCT area?
Yes, they are.
So you look for Yocto Crash Course in GitHub/VCT Labs, where VCTL is uppercase.
All right, let's try plugging in here.
So, well, go ahead and just start that. Let me get this up, and we'll see if it's usable. So before we came, because I wasn't going to try to build it while we were talking, I built some BeagleBone, Raspberry Pi, and QEMU x86 images to go with the second part of the talk. And originally we wanted to do kind of a hands-on thing, but all we got was an hour thing, so we can't really do the hands-on.
Yeah, can't really do a build in an hour.
So if you look at either, is this even working? If you look at either the Yocto Getting Started Guide, will tell you about the supported distributions and what the build requirements, what packages to install to get started. It's a little bit more than Build Essential on Debian. You need some things like Git and some other stuff, but that'll tell you. And then you can see some unsupported distributions. I'm building on Gentoo x86, which is essentially an unsupported distribution, but it works just fine. So the only issue really with Gentoo at this point was I did not have time to fix libsudo so it works correctly on Gentoo AMD 64, so you can't build OpenEmbedded easily on a native AMD 64 multi-lib box.
Okay, so you're talking about those are the systems that you use for your host?
That you will build OpenEmbedded on, yes.
So essentially, let's say, for instance, if you're using one of these non-Debian distros, then you're actually building an embedded OS that might use Debian.
No, OpenEmbedded is essentially completely independent from your build host from that perspective. It's literally going to build your own Linux distribution. So it doesn't matter whether you build on Fedora, Debian, Ubuntu, or Gentoo. As long as you have the tools installed, it's all the same. It's just whatever distribution you're more comfortable working in. If it's supported, you would want to use that. So let's see. You can also do things like build inside a virtual machine. I've done that before, and you can actually do it in a VM that you only allocate, a couple gigs of RAM and a couple cores. It'll take a little while, but you can do it. So you don't have to have a super monster 8-core build machine to build this stuff. It'll build a lot faster that way, but it still builds on a relatively underpowered machine. So you can build in a VM, you can build in a chroot, which is what I do on this machine because it's a 64-bit Gen 2, so I build inside an x86 CH root. So there's different ways you can work around some of those issues. And then every once in a while you hit things. So some of the most common build errors, there are some bitbake errors that you can get into that aren't really useful to talk about unless you hit one of them. But usually the error messages that come out of bitbake are fairly good. So you should be able to figure out if it's unhappy about something. The biggest thing is it doesn't tell you to install things like BC, which you need when you build certain kinds of kernels, and that's not listed in the build dependencies. So there's a couple of hidden build dependencies that you might hit during a build, and then you'll have a build failure. You look back up through your scroll, and you'll find, oops, command not found. And you go, oh, well, I need a package. So those are some of the one or two little things that might bite you. But for the most part, the documentation's very good. It's much better documented than most things you might be used to, Yocto in particular. And then another thing that can kill your build is if you have a network outage during the build, and if it's trying to clone a Git repository and it can't do a Git ls remote on the remote repository, then it'll give up and fail. So it'll stop the build at that point if it can't download the source code. So you can run bitbake, and we'll see a few command examples later. You can run it with -k, which will keep going past the failure and build as much as it can before it can't go any farther. If the failure was a dependency of something later on, then it'll fail again when it gets to that point.
And sometimes the network errors show up in weird ways. The other day, for example, I was having a lot of my builds failing, and as it turns out, it was a day when SourceForge was very unhappy for some reason, returning bad SSL certificates, and half the time, and the other half of the time returning HTML pages instead of code. So I see a checksum error, and it's like, okay, what's going on here? And eventually I figured out, oh, SourceForge is having a bad day.
Those are fun ones. We used to have nightly builds die because Bitbucket would stop responding in the middle of the night. So. All right, this is basically kind of what your OpenEmbedded environment looks like to a certain extent, or kind of what it is. So it's a combination of metadata, which is all those software recipes that build packages and stuff, the machine configuration, which it needs to know to build things like your kernel, your bootloader, and a few other things. Because you also tell it in the machine configuration whether your machine has a keyboard, whether it has a display, what kind of display, all that kind of stuff. So all that stuff needs to be in your BSP layer in a machine.conf file. So then the distribution layers, like we said, you can build OpenEmbedded several different ways. And you can build a couple of different distributions, or OE Core can even build distro lists. So you can build OE Core by itself without even downloading the Pocky stuff. So the Yocto reference BSP is the one we were talking about before that supports SpiegelBone, a bunch of QEMU machines, and Edge Router, and a couple other ones. Normally I would build for BeagleBone because that's what I have. I don't do a lot with QEMU. And then you have all these different software layers depending. So go to the layers index, the layers.openembedded.org, and you can find where all these guys are. But you can build an OpenStack layer if you want to. So you can use this kind of stuff for more than just embedded builds. You can build yourself your OpenStack layer and deploy it to your virtual machine cloud, right? So the main thing that you find in the BSPs, and what's of course really important, is the machine definition, kernel recipes for that machine, and bootloader recipes. So in the primary, in those core layers, the Linux Yocto kernel is kind of the main one that gets built for QEMU and BeagleBone and whatnot. But if you look in some of the other machine layers, MetaTI was the one. These are both for BeagleBone, and so that's why it's sometimes a little bit confusing. BeagleBone is here in the reference BSP. There's the Meta BeagleBoard layer that has other Beagle machines in it and BeagleBone support. And then there's the Meta TI layer that comes from the company itself, which supports all their own software stuff that you would install on TI machines. And that also has kernel recipes in it, such as their Linux mainline kernel recipe. So the one thing you don't want to do is put two BSP layers in your layers configuration at the same time, because then it gets confused about which kernel to build, other stuff. So you only want one BSP layer. There's also the Linux TI staging kernel, which is newer and a little bit edgier than their mainline kernel. And the versions will vary across the board depending on the machine and the layer. It could be as old as 3.8 is still a current kernel for BeagleBone. 3.14 seems to be the newest one in the mainline, in the core Yocto stuff now. But I've been building 3.18, 3.19 for my hardware. It's just I don't do it with OpenEmbedded. Although sometimes I do, because I put one of those kernel recipes in there for BeagleBone just because. Next. Let's see. So our environment continued. So how you configure OpenEmbedded is kind of interesting, because they have several different config groupings, and they're somewhat overlapping but different. So image features is one of them. And so when you're building an image, whether it's a tarball rootfs or whether it's an SD card image like Meta Raspberry Pi builds, it literally creates the SD image that you just DD to your card, and you're done. The BeagleBone one will build the MLO and uboot.bin and give you a rootfs tarball that you have to manually put onto your card. So it all depends on the layer and whether the upstream developers defined a BB class that creates a card image, because there's a couple other ones besides Raspberry Pi. But so you have image features that affect that particular image that you're building. You have distro features that are across all the images that you build, and you have machine features that are specific to your particular hardware machine. And then within recipes, you also have package config, which is a way to modify what a recipe produces in packages without actually modifying anything, like literally editing the recipe. You just set some package config options, and then the recipes already have the logic in there. It's like a use flag. So if you built a Gentoo package before, you know about use flags, and this is kind of similar. So it's mainly the layers are mainly basically recipe trees. It's kind of like a portage overlay in a way. So within there you'll have the recipes themselves, and those are the .bb files and bb appends. You have bb class files, which are sort of like our portage e-classes kind of a thing. You have include files that are included by recipes, and those are .inc files, because they might be included by several different versions of the same recipe. So you have your core stuff in the include file, and then you'll have a version-specific bb file that calls it, that will have maybe one or two things in it, and that's it. Um, and a lot of that stuff is, well, there's also config files too. So besides the machine.conf that you shouldn't be changing, hopefully, there are a lot of layer config files and other .conf files that you need to modify when you first set up your Yocto install so that you can build stuff. So the main two that we'll talk about in a few minutes are local.conf and bblayers.conf. So most of those packages, they pretty much all build from source. Although you can easily you can install binaries if you want. If you have some pre-built thing that you've already built for that target machine, it's very easy to have a recipe that just deploys the binaries into the root FS and you're done. But most everything is built from source. And so they're either going to pull tarballs from an upstream source, or they're going to actually literally check out from a Git repository or an SVN repository. And we in the OpenEmbedded land, there's no law that says like ebuilds that are Git ebuilds or .9 or -999 versions. That's not true in the Yocto world. So you'll have some recipes that are blah blah underscore Git, but you'll have other recipes that use Git but have a version on them, and then they'll have a tag or a commit hash that they build from. So it's kind of a big mixture of that stuff. So you'll see a lot of these live recipes that actually check out the latest, either the latest code or a given branch. Go ahead. Pardon? Oh, if in the layer index, an ungodly number, I would think. But in the core Yocto, there's enough recipes to build all those basic images. So somewhere in the several hundreds. And it depends on if you add in some of the subsidiary meta layers too, because there are some recipe layers that are inside the core Yocto and OE core that you don't enable, or that aren't enabled unless you explicitly enable them in BB layers. So it won't even look there if they're not in the bblayers.conf. Okay, next one. So the kernel selection, again, this is where it kind of gets a little bit interesting too, because you might not want the kernel that is their default kernel, either the version or the config. And so there are easy ways to change that, right? So if you don't want that Linux Yocto kernel on your BeagleBone, you can change preferred provider to the TI mainline or TI staging kernel, and it'll build that one instead. But your configuration is going to have one of these in here already, and normally it goes in there with a question mark equals, so that it only sets it if it's not already set, so that you can override it in your local.conf. So you can say, I want preferred provider to be TI staging. And then you can say, I want my preferred version to be that version. As long as that version exists in the tree, you can build it, right? And so when you build, it builds an image or a tarball or whatever, but it also builds a whole tree of packages. And so depending on whether you've configured it to build deb, RPM, or IPK packages, it'll build this tree, and then you can use that package feed from your running machine to do updates just like you would do on your normal Debian machine with apt-get, right? So you can easily make an IPK feed by pointing Apache at the top level directory IPK. And then inside the config file on your running machine, you point it to that URL, and you can update your packages that way. I've actually done that on Raspberry Pi after building, pulling off master, building again, and then I did this huge update once on the Raspberry Pi, and it downloaded like 400 packages, and it all worked. So
Well, IPK is, or O package is the package manager, and it's a very simple package manager compared to RPM or things like that. It has the core commands that you need, right? You don't need to look up weird commands like you do with apt-get to see what was installed on your machine. So it's kind of limited, but it does have the core stuff, pretty much the core stuff that you need. So, and it's a very simple package format. The one thing nice about IPKs is it's just a tarball. It's like a simplified deb package. So it has that control and data and the tarball, right? Right, it's just an AR wrapper, so you can unpack it and then look at everything inside and extract the stuff real easy. So, but you can also create these feeds if you choose that package format, but you have to look up how to do that yourself. So, any more questions? You want to ask that during Stephanie's talk on build root and Yocto? Right. So I'm not the build root guy, so it's hard for me to answer that, but I like OpenEmbedded. It's a very nice tool to use. So I mean, if you have a more specific question, something that you're interested in, I could probably answer that.
It was just sort of a comparison of the different features. Do they both solve the same problem?
Essentially, they do. Build root is just a much simpler way to do it than OpenEmbedded. It's kind of, I mean, it's not right. She'll do a better job of answering than I will.
I'll do a repeat at SCaLE.
Okay. All right. So bit-bake tips and tricks. One of the things that you can do is execute one task at a time. And so when you're developing stuff, that's a very good thing to be able to do. Similar to ebuild, the ebuild command in Gentoo, right? So you would ebuild compile your recipe to test the compile. You can do the same thing with bitbake. You can do bitbake-c and then the command you want it to run. So you can clean a package, you can unpack it again, you can go in there with dev shell, make a change, you can run the compile task. So that's for more of a kind of a developer workflow. The B argument will allow you to build a package without any dependency checking. So you give it the -B argument and the full path to the ebuild, or the recipe, sorry, I'm getting confused now. You give it the full path to the recipe, and then it'll build it, but it won't care about dependencies. Otherwise, if you use, whether you use the C command or just bitbake itself, it'll always do its dependency check before it tries to build what you told it to build. And then the big D argument will get you some debug spew. Normally now, it used to be that OE Classic would basically show you the same output as you would get from running emerge foo, right? You see all the compiler output and everything. Nowadays, it doesn't do that. Nowadays, OpenEmbedded gives you a running total of which tasks it's doing right now on which packages, but it doesn't spew all the debug to the console. It just puts everything in log files. But if you want to see it come out, you can throw -D in there one or more times and get a lot of debug spew to make it look more Gentoo-y. So, I mean, it does all the same things, like I said, the source fetching, patching, configuration, compilation. So there is a couple of special commands that aren't task commands within a recipe that you can use to say, fetch all the sources for the build I'm building. So you can tell it to download everything first and then go off with your laptop to the pool and build over there somewhere.
Or to a facility that doesn't allow internet access.
Right. So the one thing that is kind of weird about it, me being a Gentoo developer going to Yocto, is that when they package things, they package like mad. And they will split things. One recipe can generate 50 packages, depending on what it is. And the reason they do that is because you're building an embedded image. And so you have runtime depends that control whether those packages get installed on your target or not. Right? So it might build 50 packages from a given recipe, but it's only going to install the one or two that it needs to install to satisfy your image requirements. So that's how they keep their root FS very small. And they'll package up all the docs too, so that you can grab the docs package from something, but it won't install it typically. So that's kind of the big difference in how it packages. And then the image stuff, like I said, there are BB classes that do SD card images and things. So it's pretty much going to produce a JFFS2 image for the older NAND-based stuff. It's going to produce a rootfs tarball. For some machines, it'll produce the SD card image. It'll produce your kernel and module tarballs and your bootloader files that you need. And so you can manually put it wherever you need to put it. The SDK stuff is an interesting thing too. They have lots of different targets for SDK generation. So you can build a minimal tool chain that matches your build environment and then go install it on another machine. You can build a full SDK that's specific to all the software that's installed in your image. So if you're building stuff that you're going to install and run in this image, you can generate the perfect SDK that has everything that you need. There's a command we'll see coming up later for that. And then again, I think I threw in the layers index and GitHub as some pointers to some of the upstream stuff. I don't know why that's orange. That was like green or something on my machine when I was doing it.
Strange.
Did you click on all the links and make them orange?
No.
So here's our extra quick start, how you get started doing this stuff. Clone one repository, CD into the top level directory and source the environment script. Adjust your configuration, source it again, build. That's your big quick start. And that's essentially what it says in the README for Meta Raspberry Pi and for a bunch of other OpenEmbedded layers. That's basically what you get in the README. Some of them are more elaborate, but so you go through these steps, and you can, when you're done, you can just use their OpenEmbedded run QEMU script to run that image that you just built. So you point it at your, it'll also build partition images too. So you'll get an ext3 rootfs image out of some of those builds. And it's not the full disk image, it's just the rootfs partition image. So that QEMU can launch it that way. Because you just point QEMU at your kernel that you just built, and your ext3 image runs it. So BeagleBone is a little bit different. Essentially, if you want to build for BeagleBone, you would source your environment script with a different build directory, because each time you source that guy, it creates a build directory where it's going to put all the build output. And so the first time, if you source it without any argument, it creates a directory called build. So if you want to have several of them, you just tell it to make a build-rpi, a build-bbb, a build-qemu x86, and then you can have your build directories there with all the output. So you make a new one for BeagleBone, configure local.conf again, and build. And that's exactly what we did here. But I think I'm going to wait until we're done before I try hooking this thing up. So let's see if we can whip through these and then do some demo. Raspberry Pi, you need to do one extra step, right? Would be clone the Meta Raspberry Pi layer from GitHub and then go through the same sequence of steps. But Raspberry Pi should actually build right off the bat for you. You should be able to run they have a tiny, tiny hardware test image in the Raspberry Pi layer, so you can build a teeny weeny console image to test it with. So for the Raspberry Pi layer, and that's the GitHub, the new maintainer's GitHub address. I have a fork of this, but they just turned over the upstream maintenance from the original guy to another guy. So he's written a README that's actually a little bigger than several of the ones that I've seen, and it tells you what the requirements are, how you can build it, and so supposedly Raspberry Pi can build the way that it's tested and the way that I've been doing it, or with OE Core by itself, or as an angstrom distribution. So you have some flexibility in terms of how you want to do it. The BeagleBoard TI layers, the official one really is Meta TI now. The BeagleBoard.org Meta BeagleBoard layer was ahead of the Meta TI layer, I guess. It was being used by the BeagleBoard.org folks, and they had newer kernels and things in there, but I think it's less maintained now. There hasn't been any changes in the Meta BeagleBoard on GitHub for 8 months, give or take, something like that, and I think might be a more recent fork, but the TI guys at OpenEmbedded will point you to the Meta TI layer now. So there's still a couple useful things in the BeagleBoard layer, though, so if you're doing BeagleBone, you might want to look at that. I think I built originally off of one of those forks. And then, like I said, FreeScale, there's a Meta FSL, a couple different Meta FSL layers for FreeScale stuff, which is, here's an example, right? The Udo is an IMX6 quad, which is a FreeScale, same as Monboard and Qbox I and several other ones. So that FreeScale one is different than the upstream guys. You don't go through that setup process that I talked about. You basically use their repo manifest, so you don't even manually clone anything. You just run the manifest thing, and it pulls all the clones for you and sets them up in a directory structure, and they have build scripts to build their stuff, and so it looks different than the manual setup that I do for the Pocky and OpenEmbedded stuff. But you can rearrange it a little bit. It's all in how the layers are configured in your layer.conf. But this is more automated for you, right? So if you like that, you can do FreeScale stuff by running their build script and then try to dissect what they've done. I tend to like to put it together myself so I don't have to dissect it later. So kernel version and configuration. Raspberry Pi has a fairly new kernel, but if you want the latest, you do need to override and set a preferred version. BeagleBone is the same. BeagleBone, if you want to set a newer version, the newer version of Linux Yocto that's in their tree is not in the compatible machine for BeagleBone yet. It's not defined, so you have to add that as well to get it to build a newer kernel. Because BeagleBone is like this close to mainline, fully mainlined. If you're on a really new kernel, it's actually better than the older Beagle-specific ones. But so BeagleBone is super close to being mainline fully. Not quite, but almost. So, and then there are a few global config options that you can set, but they're specific. Most of them are specific to Raspberry Pi, and they were put in there by the upstream developer. So there are a few of them that you can use in the normal OpenEmbedded. Not that many, though. One of them would be at least in the older kernel recipes, they had a configuration logic so that you could set you could enable C groups in the kernel just by putting a C groups enable blah in your config file. But that seems to be not very common. They don't do that a lot. The Raspberry Pi guys have several other ones in there that are specific to Raspberry Pi. So you can set the default audio output to be the analog or the HDMI output. You can set some of the display stuff, disable the border overscan. Some of the things that you see in the Raspberry Pi config are config options in the build. But that's because the developers actually did it that way. So it's actually easy to make your own modifications to the kernel recipe as well. You can do BB appends. You can bring in your own patches, and I've done that for BeagleBone. So sometimes it's actually worth it, but it's not that hard. If you need to add your own patch, you just add them to the source URI in your BB append, because you can source URI append, right? So the source URI is what tells it what to download for that recipe, right? So it's usually a Git repo pointer or a pointer to a tarball, and then there might be a couple local files in the source URI if they have local patches or other things that they need during the build. And so you can do the same thing. I guess now with kernel stuff, you don't need to worry about MD5 some stuff, at least in the latest one with the Git recipes. There's no more MD5 sum in there. You used to have to put in an MD5 sum for the tarballs, and even in the case of a Git build, there would be like a license checksum on some piece of the license file in the source code upstream. So you could hit some change. If something changed, then it will not download it, right? Were you waiting to say something? Oh. So you can make your own custom kernel recipe, and there is an example Linux Yocto custom BB that you can look at. So just like the metaskeleton recipes, there's an example custom kernel recipe. So they're a little bit better about providing that kind of stuff. Gen 2, it's like, go do it yourself. Yeah.
So, device tree stuff is also considered part of the kernel?
It will deploy the device tree file as well as the kernel if there is one. But there just aren't that many machines that are at that level yet that you can build with Yocto. BeagleBone might be the only one I've seen. Freescale, I haven't built that stuff yet for a while anyway. Yeah.
Yeah, can you back up a little bit? I'm missing something that, from not being familiar with OpenEmbedded, is that, looks like Yocto allows you to modify your recipe, uses a recipe in order to be able to build an image that closely matches the hardware you're trying to run on. But what about software besides the kernel? Okay, so what are some of the restrictions or options that you generally get? What do you actually get when you build? And it looks like
it depends on the image that you build.
Okay,
so that's the main thing. And when we look at some of the images, the files are very small because all the definition stuff is kind of buried in the BB classes and the config, the overall config. So normally if you're really doing something custom, then you would probably want to create your own package groups and your own image files that will install those package groups. There are some existing package groups like for X11 and some other stuff. And like I said, the image features is really how you configure the images in a broad sense. So you would tell the image feature, you would say in image features you would add X11. And then it would install like the basic X11 package groups for you.
So this sounds like then this would be most useful for building a single purpose type of an app, like an app device.
Well, that's one obvious use case for it, and that's kind of one of the primary drivers, right? Because the original guys that did this were working on the Zaurus. at the
Because
time.
one of the strengths of using or having access to a regular distro, for instance, is the large library of packages that they're already
Oh, right.
pre-built.
Right, and so that there's a pretty large universe of recipes that you can install in here too. There's a fairly small core in Pocky that basically is enough to get X11 and maybe with GNOME and stuff. If you add some of the other layers, there's an XFCE layer, there's a GNOME layer, there's Qt5 stuff. So it all depends on what you want. It's not going to be a general purpose distribution unless you build an image that has packages up the wazoo in it, right? And so for my fork of Raspberry Pi, I made a desktop layer that goes with it. So I have a layer on GitHub that has a bunch of packages in it that are defined, and so it makes a lightweight image that has OpenBox, Tint2, and a bunch of lightweight applications that all get installed in the image along with my LIRC daemon and MPD and the audio stuff that I want in there. Even though it's headless, it has a desktop. So you can do it. We could take a look at that if you want to.
I also noticed that even though it says that there was some documentation that seems to say that you can create different types of packages for like RPM or DES or whatever.
Well, it'll build everything as that package type that you define in your config file. So if you say you want package class deb, then all the packages that come out are deb packages.
So what about some of the resources that are already available? Are they mostly DEBs, or are there pretty evenly distributed RPMs, DEBs, and whatever?
I mean, none of the stuff that you would get from Yocto, Pocky OpenEmbedded, none of that's packaged at all.
Okay.
It's basically, it's all stuff from GitHub essentially, or a tarball that you download. Do they? There's I don't do that either, but a few of the Angstrom's still active, and that's one of the earliest OpenEmbedded distributions that there was, way back when on those old iPac handheld PDA things. Oh, yeah. But so I mean, yeah, it is special purpose customizable, but it's very flexible. And so you can make a bigger image if you want, but most people are trying to make a tight image that is focused on whatever they're doing. And so like if you're building a surgical camera, you want the packages you need for the camera functionality and stuff, and you don't care about other stuff. Let's see, one more. So deploy tips. Like I said, when we deploy this stuff, it all depends on what comes out of the build, and that's going to be different for the different machines. So in the case of a Raspberry Pi, you'll get a big long file name with this extension. And so it's pretty obvious that that's the Raspberry Pi SD card image that you want to DD to your SD card, right? The other ones, like I said, you get a root partition image that you can boot with QEMU, or you get a tarball or a flash image. It all depends on which machine that you're building for. And so one of the things that you might run into is like, well, is U-boot looking for the kernel in the boot partition, or is it looking for it on the root partition? And so in the case of BeagleBone now, it's looking in the root partition. So the only reason that you have a boot partition on a BeagleBone card is to load the bootloader. And then the bootloader looks over in the other partition, grabs the kernel out of the boot directory, and you're good to go. But it depends. Again, in some cases it might be looking for it somewhere else. So it's kind of specific to a given machine and a given group of developers that decided what they wanted to do. So -C deploy is a good one for when you're hacking on the kernel. So you've got a build, the kernel's not right, you want to make a change to the kernel, you go ahead and you make the change, and then you do bitbake -C deploy which spits out the kernel to your deploy directory, and you don't have to wait for it to go through the whole do root fs procedure to build a whole root fs again. So, and what you can also do is create a custom deploy task depending on what your needs are. And that again, I go back to the surgical camera thing. We did a few custom deploy things for that project just because, you know, a need comes up and you need stuff in your image, and so you can make custom deploy tasks that go through and do some weird things to the image before it puts it out. Again, we talked about the local IPK package feeds, so you can actually update your packages on the running device without doing a whole new deploy of everything. The SDK tools, again, I talked about the cross toolchain. The meta toolchain target is the one for a minimal cross toolchain that matches your build environment and build target. But if you run bitbake image-c populate SDK, it will take that meta toolchain thing and it will add the headers and libraries and all that stuff that you need from every piece of software in your build image. And so you'll end up with a nice big fat SDK that has the toolchain, all your build dependencies, and you just install it on your workstation, do cross builds. So image tweaks, like I said, the image features are fairly common, but there's a few extra image features that pop up that you can use also to tweak your image. And if you want to, you can define your own stuff to tweak. Because if you look at my fork of Meta Raspberry Pi, it has config options that the other guy, upstream guy, doesn't have. Because I wanted my build to come out with a PST default time zone, and I wanted some other stuff. So I made a few options, and so in my config file I say what my time zone is. Because otherwise you get whatever it thinks the default is. Okay, and so the two main ways to debug this stuff is GDB server running on the target machine and GDB running on your local machine. But now there's also Eclipse plus their TCF agent. So Eclipse has a whole embedded development thing going now. I know Eclipse wants to develop everything, but they have fairly decent support for embedded development now, and that TCF agent is already in Yocto Pocky. So all you do is enable Eclipse debug in your config file, and you get what you need. So it's actually pretty nice. So let's see now, we're almost done here. Let's see if we can bring up Toaster. Does anybody have any questions?
Bloat in your system, and the bloat takes up space and potentially time.
Right.
Does OpenEmbedded or Yocto give support for the problem of getting an embedded Linux system to boot faster?
Not specifically that I know of. I mean, you can still choose between System D and a normal System 5 init kind of setup. But typically, if the work that you need to do to optimize your boot like that is on you. I mean, they have the tools to profile it, but they don't have any built-in facility to generically optimize your machine's boot. Right, okay. But I did build it specifically without systemd in mind anyway, so.
Thank you very much for coming. Oh, you got it? Any more questions? Any more questions? Thank you very much for coming.
All right, cool. I think I liked it better with not messing with my video.